Hi everyone, welcome to the ATAR Notes QCE Chemistry Unit 1 and 2 July lecture. So before we get started, I'll just tell you a little bit about ATAR Notes and what we do. So ATAR Notes provides a bunch of free resources which are here to help you get the best possible results you can in your QCE. So we have heaps of study notes online, and these are all free and downloadable. We also have all of our lecture series which run throughout the year to help you stay on top of all your study. We have online discussion Q&As, videos which provide lots of engaging online revision, newsletters which can keep you up to date with all the latest information, an ATAR calculator to see if you're on track for the ATAR that you want to receive, articles which provide tons of useful study strategies and tips, and heaps more, so check out our website. We also have some more paid resources, and these are all created by elite students and are designed to help you get the best possible marks. And so we have TuteSmart, which is online tutoring from recent Year 12 graduates. We've also got the study guides, and these are printed revision materials with lots of top tips. They've got lots of set out notes and practice questions to help you get the best possible marks. And then we've also got Ed Unlimited, which is our online platform, which has lots of study guides, practice questions, and practice exams all in one online platform. So that's really great. So this is just a bit of an overview of what we're going to be doing today. So we'll start off with the VSEPR theory. Then we'll go on and talk about polarity, then intermolecular forces, then we'll talk about gases, aqueous solutions, and solubility, and then we'll do a little bit of talking about acids and bases and rates of reaction. So first of all, we'll start off with talking about VSEPR. So the VSEPR theory is otherwise known as the valence shell electron pair repulsion theory. And so this basically talks about our 3D structure of molecules and how they are arranged in space, as opposed to it being a Lewis diagram. And so as we can see here on this particular diagram, we can see that we've got a methane molecule, and then we can convert it into a VSEPR theory in which it forms a triangular type molecule shape. And so these are going to have these structures based on non-bonded atoms avoiding each other due to mutual repulsion of their bonding electrons. So this is talking about where certain non-bonded electrons don't want to be nearby each other, so they will evenly spread each other out because they're repelled by each other's electrons. Then we can also consider the bonding electrons, and they're repelled by lone pair electrons. And so that's talking about where we have a lone pair of electrons which aren't bonded to anything else, and they cause a bend away from the rest of the molecule because these particular electrons repel the rest of the molecule due to the electrons in the other parts of the molecule. And so these lone pair electrons are also going to be repelled by other lone pair electrons. So if you have multiple lone pair electrons in a molecule, then they're going to be repelled by each other, which further pushes the rest of the molecule away from each other, but also pushes those lone pairs away from each other, which is also going to affect the structure and bonding of the particular molecule in its 3D structure, compared to where we look at the Lewis structure, which is very 2D and just a flat representation. And so we need to consider degrees of repulsion. And so these degrees of repulsion are going to be dependent on these factors which we spoke about earlier, where we considered the non-bonded atoms, the bonding electrons, and our lone pairs. And so The effect of the additional repulsion from those lone pairs is going to be demonstrated by differences in bond angles, and we can specifically see this here in methane, ammonia, and water. And so we can see with methane, we've got this 109.5 degrees separation of angle between the hydrogens which are bonded to our central carbon atom. And so this is because all of the hydrogen atoms around the central carbon have evenly spread themselves out such that they've all attained an 109.5 degrees between each other. And this is because there's 4 hydrogen atoms which surround the carbon atom, and so because there's 4 of them all surrounding this one carbon atom and there's no lone pair to repel them away, it's going to result in the molecule being structurally even in its 3D structure. We can then consider ammonia, and ammonia has an 107 degree angle between each of the hydrogen atoms that are spread flat or slightly downward angled from the nitrogen. And so this is because ammonia has a lone pair from the nitrogen atom. And so that's because nitrogen has 5 valence electrons, but we can see in ammonia, hydrogen has only been bonded 3 times. So there's only 3 hydrogen atoms bonded to the nitrogen in ammonia. And so this means that all of the hydrogens have achieved a stable octet because they've only got 1 in their valence shell. So if they bond with nitrogen, they've then completed their valence shell of the first valence shell to have 2, which would achieve what we call a stable octet. But with the nitrogen atom, it would need to have more atoms to bond to it in order to bond to the 2 atoms on the top of the molecule which remain. So obviously nitrogen has 5 valence electrons. It's achieved an extra 3 from each of the hydrogen atoms, which gets it to 5, which gets it to the stable octet. However, there's 2 unpaired electrons, and those 2 unpaired electrons are sitting at the top of the ammonia molecule and are repelling the hydrogen atoms of that molecule because they don't want to be near that because of the repulsion theory. And so that forms this downward structure where the nitrogen electrons on the top from the lone pair repel the hydrogens downwards. We can then look at water, and so water is just H2O, so we've got our central oxygen atom with a hydrogen bonded on either side. And so this has a 104.5 degree angle, and that's because there are 2 lone pairs. So that's because we have the valence electrons in the oxygen mean that there's only pairing for 2 of oxygen's valence electrons, and so that leaves 4 unpaired electrons. And so these 4 unpaired electrons are sitting at the top, they're repelling each other, and so they will sit angularly on either side of the oxygen atom, but then they're also repelling the hydrogen atoms which are branching off from the oxygen, and so hence pushing them downwards, forming in that 104.5 degree angle. And so that's important to notice that we have a trigonal pyramidal bond angle, which is that 109.5 degree angle, which we can see in methane. With water, we can see that that is a bent arrangement, and we can see we have a similar pyramidal type arrangement with ammonia. And so even though the parental geometry is the same, the overall geometry differs due to the electron pairing. And so the bond angles have been shortened because of the presence of lone pairs. And that's just because of our repulsion theory, where the lone pairs push the rest of the atom away, shortening those bond angles. So we want to learn how to draw Lewis diagrams using VSEPR. And so the fundamental process of doing this is not that difficult. We just want to first focus on drawing the Lewis diagram and then understanding what the parental geometry is in order to then understand the repulsion that's occurring in these molecules. And so the first thing we want to do is determine the correct Lewis diagram for the molecule. So it doesn't need to be the correct shape, it just needs to show all of the atoms and what is going to be bonded by what. We then want to determine what the parental geometry is. So that's understanding where the bonded atoms are going to be located and where the lone pairs are going to be located. Because it's important to understand what is bonded to what so that we know where things can disperse off, and also we want to understand if there are lone pairs present, because we want to know if there's 1, 2 or no lone pairs, as this will tell us the degree of repulsion which will occur and whether the molecule will bend in such a way that the bond angles will decrease. We next want to then chop off the arms where the lone pairs are in the appropriate places according to our rules that determine molecular geometry. So that's understanding where we need to remove things in accordance with those lone pairs. And then the final thing is we want to consider the added repulsion of the electron pairs. So how the electron pairs are causing the repulsion and to what extent they are causing repulsion due to how many lone pairs are present. So these are our molecular geometry types. And so these are all of our bond angles and the molecular geometry names, and then a little diagram to represent what they will look like. So we can see our first one here is a linear molecule. So linear molecular geometry has a 180 degrees bond angle. And so this is our molecules where they're completely straightly bonded to each other, and there is complete stable octet that's been attained without the presence of any lone pairs. So this means that the molecule in pink in the middle on the linear bond angle is a different atom to the white atoms, but they've all bonded in a straight line and have used up all of their electrons in order to bond together, and so have no lone pairs, so there's no repulsion, so there's no need for the molecule to bend away from anything because there's no repulsion coming from a lone pair. And so this just means that the molecule stays completely straight. There's not really any bond angle, so we say that the bond angle is 180 degrees. Our next one is bent, and so the bent molecular geometry is looking at a 104.5 degrees bond angle. And so a 104.5 degrees bond angle is typically going to suggest that we have 2 lone pairs present. So that means 4 unpaired electrons. These electrons pair up and form 2 lone pairs, and so these sit on either side of that central pink atom and repel the white atoms downwards in such a way that it forms a 104.5 degrees angle because the lone pairs are repelling those other atoms. And so this is something that we see in water, which we looked at a bit earlier. Our next one which we see is trigonal planar. And so trigonal planar has a 120 degrees bond angle. And so we can see that this is another, much like the linear molecule, there's no presence of unpaired or lone pairs in this particular scenario. And so we don't have any downward repulsion that we can identify in this molecule. And so as a result of this, the molecules are spaced evenly from each other all around the central atom, so the central atom being the pink atom, and so they're all spaced evenly around resulting in this 120-degree bond angle between all of them, because they central around in a circular pattern, and so all of the angles around the central atom add up to 360 because there is 3 atoms surrounding all angles, that can be divided by 3 to get 120. Our next one is tetrahedral. So tetrahedral has a 109 degrees bond angle, and so that's because much like our linear and our trigonal planar, there's no presence of a lone pair, and so this means that all of the atoms stay centrally located around the central atom, and so we can see that they all branch off at an equal distance around, and so this equal distance around means that we don't have to worry about any changes or any repulsion. Our final one is the pyramidal arrangement, and so the pyramidal arrangement has a bond angle of 107 degrees between each of the branched atoms. And this is because we do have the presence of a lone pair. And so this is quite commonly seen in ammonia, where we have that lone pair on the top. And so what the lone pair does is it repels all of the atoms, all of the white atoms, which we can see, downwards from that central pink atom, because the lone pair on the top is repelling them downwards, and because there's obviously electrons in those white atoms, they're being pushed downwards because they're repelling, because like is going to repel like in this case. So now we just have an example question. So if you're watching this live, feel free to take a moment to try these out yourself. So we'll just give about 1 minute for you to try these out yourself to figure out what the molecular geometry and bond angles of the following molecules are. And then if you're watching the recording, then feel free to take this time to try these out on your own and pause the video if you need. But basically we want to determine what the bond angles of CH4, NH3 and H2O will be. So I'll give you about 1 minute to try that on your own. Okay, so that's about 1 minute up. So these are our answers here. So we've got CH4. So CH4 is otherwise known as methane. And so this follows a tetrahedral type shape. And so it's going to have 109.5 degree angles between them. And so we can see this here. We have our Lewis diagram, which has then been converted to show our 3D arrangement and show our bond angle. And then we've also got our VESPA 3D model, in which we can see this tetrahedral shape which has been formed. Our next one is ammonia, or NH3, and so we can see that this has a pyramidal shape and has a 107 degree bond angle. And so with this here, we can see we've obviously got our Lewis diagram, and then we've got our 3D VESPA diagram. And so we can see that we've got this lone pair here on the top, and this lone pair is repelling the hydrogen atoms downwards, and that is resulted in this 106 or 0.7 or rounded up to 107 degree bond angle. Our final one is H2O. And so this one has a bent structure, and that means that it has a 104.5 degree bond angle. And so we can see our Lewis diagram here showing the two lone pairs, and these two lone pairs have repelled the hydrogens downwards. We can also see that here in our 3D diagram, which shows that these lone pairs are repelling the hydrogen atoms away from them. So now we're going to move on to talking about polarity. So polarity is basically known as the difference in electronegativity between two atoms, and so that's going to determine what the polarity of the bond is, because we can have different extents of polarity depending on that difference in electronegativity. So typically, the greater the difference in electronegativity, the more polar the bond will be. And so polarity basically just gives us a representation of the distribution of electrons within a bond. So whether the electrons are going to be more attracted to one atom or the other in that particular bond. And so it's really important that we look in the data booklet and we can look at our electronegativities and our first ionization energies of selected elements page of the data booklet. And so this basically gives us a periodic table which shows us the electronegativity, which is the number just below the symbol, and basically those are the electronegativities of each individual atom, and so we can then use those electronegativities when we have a bonding situation in a particular molecule or compound, and we can determine the difference between the electronegativities, and that can tell us whether the bond is going to be non-polar covalent, polar covalent, or ionic. So typically we say that an electronegativity difference of 0 to 0.4 is going to be non-polar covalent. A electronegativity difference of 0.4 to 1.7 will be polar covalent, and then 1.7 or greater will be considered to be ionic. So for example, if we had carbon bonded to hydrogen, we can see that hydrogen has an electronegativity of 2.2, whereas carbon has an electronegativity of 2.6. So we do 2.6 minus 2.4, and that will give us 0.4 as our answer. So we can say that a carbon to hydrogen bond is on the borderline of non-polar covalent and polar covalent, as it's 0.4, but depending on where you look at the data for what people say, some people say 0.5 to 1.7 is considered to be polar covalent, and so typically a carbon to hydrogen bond is considered to be non-polar, just because 0.4 is obviously at the lower end of polar covalent and at the higher end of non-polar covalent, so we're more tending towards saying that it's going to be non-polar. And the properties that a carbon to hydrogen bond displays are not representative of a polar covalent bond. They follow much like the non-polar kind of properties, and so hence we consider that to be a non-polar covalent bond. Whereas if we were to consider an oxygen to a hydrogen, we could do 3.4 for oxygen minus 2.2 for hydrogen, and so that would give us a 1.2 difference, and so that would then suggest a polar covalent bond. So the polarity of a molecule is given by both the polarity of the constituent bonds, but also the molecular structure. And so polar covalent bonds give a dipole vector, and so that's always drawn as positive to negative. And so the 3D structure must permit the sum of the vectors to not equal 0. So basically we have these temporary dipole moments which form, and so we don't want these dipole moments to equal 0, otherwise it's no longer considered to be polar. And so if we're considering something like a carbon dioxide molecule, that's going to have an even spread of electron pull from each side. So because we have an oxygen pulling from one side on the carbon and an oxygen pulling from the other side on the carbon, no matter what the polarity of the individual bonds themselves is between the carbon and the oxygen, because they're equal on both sides, it's going to result in a non-polar molecule because it's completely evenly dispersed and there's no temporary dipole, no temporary pull of electrons is going to any particular side of the molecule. And so that means that in order for a molecule to be polar, it must satisfy two main rules. And so these two main rules are that the molecule must contain at least one polar covalent bond, and the second one is that it must have a molecular structure such that the sum of all of the vectors of each bond dipole does not cancel out. And so this will then result in a molecular net dipole. And so a molecular net dipole is just going to mean that overall one side of the molecule is more positive and the other side is more negative, and with the more negative side being the side at which more of the electrons have been attracted to due to that difference in electronegativity being focused on one side of the molecule. And so that occurs in a non-symmetrical molecule. So now we're going to go on to talk about intermolecular forces. So intermolecular forces, we have three main types. And so intermolecular forces are basically just any forces that are existing between molecules that hold them closely together and maintain a strength and structure. So intermolecular forces are really important because otherwise without them, everything around us would just completely fall apart. And so with our intermolecular forces, they're basically the forces that hold all molecules together and provide them with a great deal of structure. So consider like the chair that you're sitting on. Without intermolecular forces, it would just be a whole bunch of separate atoms and it basically wouldn't be a solid. But what intermolecular forces do is they attract all of those atoms towards each other due to differences in charges and temporary and permanent dipoles, and that holds those atoms together at various different strengths to create molecules that stick together to then create materials and structures. And so then that results in our different states, so the solid, liquid, and gaseous states, because we would know that in a gaseous state, obviously they're going to be a lot less attracted to each other, so they're all just bouncing around as a gas. In our liquid state, they're somewhat attracted to each other and they're able to stay reasonably fluid because they're not overall very compacted. And then in the solid state, they are all very well compacted together. And so this is providing that solid structure. And so our three main types of dispersion forces which we need to talk about is, our three main types of intermolecular forces which we need to talk about is dispersion forces, dipole-dipole forces, and hydrogen bonds. And so it's really important to note that these are molecules having interactions between each other. They're not actually bonds like as such which we see within a molecule itself. So these are only temporary and they can be broken, unlike with our molecules, it's much harder to break apart a molecule. And so we can consider that these can be broken in order to boil off certain samples and things like that. So our first one, which is our weakest one, is the dispersion forces. And so these occur between all molecules, and so that includes non-polar molecules. So often a lot of the types of intermolecular forces are going to require polarity or at least some difference in electronegativity due to dipoles in order to have that attraction between the molecules. But with dispersion forces, these will occur between all molecules regardless of their polarity. And so this is the weakest type of intermolecular force, because obviously if there's no difference in polarity to cause that attraction between the molecules, there's not going to be that partial positive, partial negative to an extreme extent, which is going to cause an attraction. And so hence it's going to be a lot more of a weak attraction between them. And so there's going to be constant changing distribution of electrons within the molecular electron cloud. And so that's what results in these dispersion forces, because the constant movement of the electrons around them means that there's temporarily always going to be negative and positive parts of the molecule which are changing. And so that means that other positive and negative parts of other molecules which are changing are able to be attracted to those other molecules. And so there's a temporary dipole, but this can obviously be separated quite easily, which is why it's the weakest type. And so this momentary uneven distribution causes uneven distribution in adjacent molecules. And so this differing charge is then what's going to cause that electrostatic attraction, and hence that temporary dipole. And then the larger the molecule is, the greater the strength of the dispersion forces will be. So that's really important to note, is that the bigger a molecule becomes, the more dispersion forces it will have. And so that's something really, really important to remember, because they bring that up in the exam a lot, but also it's just something general that's good to understand about molecules, is that as they get bigger, intermolecular forces will typically increase as well. And so their properties will become stronger, they can build stronger materials, and that's because there are more electrons present in each individual molecule, and so more electrons means more partial negative can be formed, which means that more partial positive can be formed, which means that there can then be more attraction of that partial negative to that partial positive in that temporary dipole. Our next one is our dipole-dipole forces. And so these will only occur between polar molecules. They're the second weakest type of intermolecular force, but they're still reasonably strong. And so these occur when there's a constant uneven distribution between electronegative atoms in a polar covalent bond. And so this causes an electrostatic attraction between the adjacent molecules. And so this is because this temporary dipole, which we were talking about before, is no longer there, or it's still there to an extent, but then we've also got this permanent dipole where we've got part of the molecule is permanently more attracts more electrons towards it, such as in chloromethane. We have this temporary attraction of electrons towards the chlorine, because chlorine is more electronegative than the carbon, and so it's going to pull the electrons towards it more, resulting in the carbon having more protons towards it and the chlorine having more electrons towards it. And so that means that the chlorine of one chloromethane molecule is going to be attracted to the carbons, the partially positive carbons of the neighboring chloromethane molecules. And so that then provides that attraction due to that constant uneven electron distribution and that permanent dipole which is being formed. And so these dipoles, these permanent and temporary dipoles, the temporary dipoles are not represented with a symbol unless it's specifically stated to show that there's a temporary dipole being formed at any point in time. But a permanent dipole, when showing attractions between molecules, is represented by this symbol with the positive or the negative. And so it's showing that we've got a positive where our protons are centered and a negative where our electrons are being centered. Finally, our strongest of the intermolecular forces is what we call our hydrogen bonds. And so it's important to not get these confused and think that they are a bond, because although they are called hydrogen bonds, they are still an intermolecular force. So then there's no actual bonding that has been formed, it's still just an attraction between molecules. However, it's very strong, and so that's why it gets called a bond. And so it is the strongest of the covalent intermolecular forces when we're not considering ionic attractions. And it's a permanent interaction between the most highly electronegative atoms and a hydrogen that is bonded covalently to a very electronegative atom. So that very electronegative atom being oxygen, nitrogen, fluorine, or sulfur. And so when you have this hydrogen bonded to one of these atoms, it means that there's this very, very large difference in electronegativity, which then results in this permanent dipole being formed. But not only is it just a permanent dipole, it's an extremely strong permanent dipole. So for example, in a water molecule, the oxygen is going to be a lot more electronegative than the hydrogen, and so there's going to be a lot more attraction of the electrons towards the oxygen than towards the hydrogens. And so that means that the oxygen part of each water molecule is going to be very, very negative, and it's going to have lots of electrons attracted to it, whilst the hydrogen part of the molecule is going to be very, very positive and going to have a lot of protons attracted to it. And so this means that there's electrostatic attraction because there's local uneven electron distribution. And so what this means is that the local even electron distribution means that the very, very positive part where the hydrogens are can be attracted to neighboring water molecules on the oxygen, so on the very, very negative part where the oxygen is. And so this allows these molecules to be attracted to each other, thus forming the hydrogen bonds. And so molecules can often have multiple different intermolecular forces. So a molecule with hydrogen bonds typically also has dipole-dipole interactions and will always have dispersion forces. So we remember that every molecule is always going to have dispersion forces. It's just whether it also has dipole-dipole interactions and hydrogen bonds too, or whether dispersion forces are the extent of its intermolecular forces. We also want to consider larger molecules because they are going to have greater dispersion forces. And so this effect is often going to be insignificant though when we compare the effects of additional hydrogen bonds or dipoles. And so this is because although a molecule such as ethane is going to have fairly low intermolecular forces, then when we go up to something like octane, that's going to have a lot greater intermolecular forces because it's got greater dispersion forces. However, if we're comparing something like octane with something like ethanol, we know ethanol has a hydroxyl group. A hydroxyl group is an oxygen bonded to a hydrogen. And so remember that oxygen bonding to hydrogen causes a hydrogen bonding, And so hydrogen bonding is going to be so much stronger than considering a large alkane type molecule like octane. And so although octane is going to have strong dispersion forces because it's a large molecule, something like ethanol with hydrogen bonds, although it's only very small, will have a lot stronger intermolecular forces because its extent of intermolecular forces with the hydrogen bonding is a lot greater than the extent of strength of a dispersion force. And so the overall strength of these intermolecular forces is going to determine the molecule's physical properties. And so these physical properties are going to include melting point, boiling point, vapor pressure, and solubility. So with melting point, as the intermolecular force strength increases, there will be greater melting point. And so this is because in order to melt a molecule, you have to separate the intermolecular forces between the individual molecules. And so this is then what allows it to go from solid. You then separate all those intermolecular forces and the molecules are able to spread out, thus melting. And then they go on from being melting and being a liquid to then being boiled if you continue heating them. And so boiling will also require the remaining intermolecular forces in the melted state to then be separated further so that it can then be turned into a gas. And so this is because we are applying heat energy to these particular substances in order to break the intermolecular forces. And so the stronger the intermolecular forces are, the more heat energy which needs to be applied to then break those intermolecular forces. And so that's why if there is a stronger intermolecular force, you're going to require more heat in order to melt and then boil that particular substance. We can then consider vapor pressure. So vapor pressure is the likelihood of a molecule to evaporate. And so vapor pressure is inversely correlated with boiling point when we're considering intermolecular forces, because if we consider boiling point is turning something from a liquid to a gas, and vapor pressure is basically the same concept. It is how likely we are to evaporate something. And so basically the opposite, because it's how likely we are to evaporate something. And so in order to evaporate a particular molecule, we separate the intermolecular forces, and so as the intermolecular force strength increases, it's going to be less likely to evaporate because the molecule is going to be less likely to separate due to those strong intermolecular forces, so it's going to be less likely to evaporate away. Our final one is solubility. So solubility is considering how likely our particular substance is to dissolve within another solvent. And so this is considering solubility in water, because with solubility in water is obviously polar. And so we know the concept of like dissolves like. So like dissolves like is going to mean that polar solvents, such as water, will only dissolve polar solutes. And non-polar solvents, such as our alkanes, will only dissolve non-polar solvents as well. And so it's like dissolves like. And so when we consider solubility, we're specifically considering solubility in water. So water being polar, the stronger the intermolecular forces become, the more soluble our molecules are going to be. So we're now going to do some example questions. So again, like we did before, I'll leave you guys a few minutes to try these on your own, and then we'll go through the answers together. So our first question is, why does increasing intermolecular forces affect the physical properties of substances? And then our second question is, what are the intermolecular forces that are acting on H2O, CO2, and NH3? So I'll give you 2 minutes to try those questions on your own, and then we'll talk these through together. Okay, so we'll now go on to the answers. So with our first one, we can see that physical properties are going to be affected by the strength of intermolecular forces. And so melting, boiling, and freezing points are going to increase as the intermolecular forces increase, whilst vapor pressure is going to decrease as the intermolecular forces increase. And then for question 2, so our first one was H2O. So H2O has both dispersion forces and hydrogen bonding. And so this is because we've got that hydrogen bonded to the oxygen. And so that is obviously got a very, very large electronegativity difference. So that results in the hydrogen bonding. And it also will have dispersion forces just because we know every molecule displays dispersion forces. Our second one was CO2. So CO2 does not have a large difference in electronegativity, nor does it have an unequal distribution of electrons because it is a completely symmetrical molecule. And so hence it will only have dispersion forces. Our final one is our NH3. And so NH3 has both dispersion, dipole-dipole, and hydrogen bonding. And so this is because NH3 will display dispersion forces as all molecules display dispersion forces. We know there's definitely hydrogen bonding because we have a nitrogen, which is a highly electronegative atom, bonded to hydrogen. And then we also know that we have a dipole-dipole interaction because we've got that lone pair at the top. And so this is relating back to our VSEPR theory, where we know we've got that lone pair which is repelling the molecule downwards. And so because the molecule is being repelled downwards due to that lone pair, it's forming these these permanent dipoles when it's being pushed downwards between each of the hydrogen atoms and the nitrogen atom. And so hence we have dispersion forces, dipole-dipole interactions, and hydrogen bondings in NH3. And so another point I want to consider and bring up with these is which one's going to have the strongest intermolecular forces. And so out of CO2, H2O, and NH3, we can see that NH3 has the most number of intermolecular forces. And so it has dispersion, dipole-dipole, and hydrogen bonding. And then when we compare that with water's got dispersion and hydrogen bonding. So that will have a little bit lesser of intermolecular forces, but it won't be as weak as something that is very weak like carbon dioxide. And so we can see carbon dioxide will have the lowest intermolecular forces out of all of these particular molecules. Water will have the next highest, and then ammonia or NH3 will have the absolute highest. And so that's just because of the compounding effect of all of the intermolecular forces adding up. We're now going to talk about gases and their kinetic theory. So with gases, we know that gaseous particles have a high degree of molecular motion. And so this is due to kinetic energy. So because the kinetic energy provides each gaseous molecule with energy, they're able to move around quite easily and quite effectively. And so these particles are going to be in constant motion, and they're going to undergo collisions due to this constant motion, because they're all moving around so quickly that there's no possible way that they're not going to collide. And so they're going to be undergoing these collisions with other particles, but also the surface of the container which they are contained within. And so if they're not contained within a container, they'll just be colliding with things in the area around them. And so temperature is going to be a measure of the average kinetic energy of all of the molecules in a particular system. So the purpose of measuring temperature in a lot of chemical applications is to determine how much chemical energy and how much kinetic energy is present in that system. And it's also a way which we measure how much kinetic energy or how much chemical energy are we providing to this system. And so hence, due to this, as our temperature increases, the average molecular kinetic energy is going to increase. And this is because the frequency and the magnitude of the particle to container or particle to surrounding objects collisions is going to increase. And so the particle container collisions are going to be measured as pressure, or particle to surroundings collisions, and these are measured as pressure. And so we can consider this diagram on the bottom left. The more particles which you have in there, the higher the pressure will be, because there's going to be more rebound from the edges of the container. And so we can also see that with the bottom in the blue and red diagram, where on the bottom left we've got lots of blue particles, and so the lots of blue particles, they're all going to be colliding a lot, and they're going to be colliding with the container a lot, and so there's going to be quite high pressure in there because there's not a lot of space for the gas to occupy. Whereas if we look at the red on the right, we can see that there is a lot fewer particles for the same amount of space. And so if we have a lot fewer particles in the same amount of space, that means that we're going to have a lot lesser collisions, a lot less frequency, and a lot less magnitude of these collisions. And so there's going to be a lot lower pressure. And so because there's a lot lower pressure, they'll also be correlated with a lot lower temperature. And so we can see that increased temperature is then going to result in an increased pressure when we're considering a system of constant volume. And so we can now make assumptions about ideal gases. And so an ideal gas is a theoretical gas that abides perfectly by the ideal gas law under all conditions. And so all conditions referring to temperature and pressure, and that's also going to be at a constant volume. And so these ideal gas assumptions are purely just assumptions, and they're ideal. So what we know about ideal gas assumptions is that real gases don't behave in that way at all, and typically don't belong to the ideal gas criterias. But we do need to know the assumptions of ideal gases, because we can apply concepts surrounding the assumptions of ideal gases to our understanding of real gases. And so our main assumptions of ideal gases are that the collisions between gas molecules are elastic, and their molecules are going to have frictionless motion, so they don't lose any energy ever. And so we know that this is not true with a real gas, because the collisions are not going to have frictionless motion, and energy will be lost when these molecules collide. The second one is the total volume of the individual molecules on their own is significantly smaller than the volume that the uncompressed gas actually occupies. So this is commonly applied to real gases, because we know that the gas that it occupies is going to be a lot smaller, because when we consider the gases, they're all going to be, the gas molecules move around a lot, and so if we're taking gas as a substance, it's going to occupy a lot more area due to its movements than the individual molecules themselves, because the individual molecules themselves are going to be quite small, but once they're moving around, they're taking up more space in order to maintain their gaseous state. So if we were to overly compress them, they would likely be able to compress into a liquid, and that's obviously then directly correlated with that temperature increase as well, because we know as temperature increases, it can likely compress to a different state. And so the third one is there are no intermolecular forces acting on the molecules or their surroundings. And so with ideal gases, that is our assumption. However, we know that with a real gas, there's always intermolecular forces acting on every molecule, whether that just be dispersion forces or whether that actually include like our dipole-dipole interactions and our hydrogen bonding. And so we know that the real gas is going to behave a lot more differently than the ideal gas, because if there's those attractions between the molecules are more likely to clump together in a way, although in their gaseous state, because they are quite movable and quite kinetic, they're obviously not going to clump together as such into a solid, but they will have relative attraction to them, unlike in an ideal gas where they're all going to stay fairly evenly spaced apart. And our fourth assumption is that the molecules are always moving, and that the distances between all of the molecules in the gas are going to be greater than the average size of the molecules. And so we know that the first part is definitely true, because we know that gaseous molecules are always moving. We know that all molecules are always moving. Even in a solid, we still have those small movements. But we know that gaseous molecules are particularly kinetic and move quite a bit. However, we know that the distances of all the molecules in the gas are not always going to be greater than the average size of the molecules. And that's because in an ideal gas, we're assuming that the gas molecules are not really moving around significantly. However, in a real gas, we know that the molecules are moving a lot, and they have motion in which they're going to be colliding excessively and then losing energy from that point. So upon those collisions, obviously the distance between the molecules is going to be changing and is going to be coming closer. and so that part doesn't necessarily apply to a real gas. And so as a result of all of these assumptions, we can come to the conclusion that gases cannot become liquid at room temperature. And that's just based on the assumptions of the ideal gases, and how we can apply those to real gases in order to then know that they can't become a liquid at room temperature, despite not fully following the ideal gas laws. And so when we consider gases, we need to consider the variables which describe gases. And so we have 4 main variables, which these are. And so these include a number of gas molecules, which will be measured in moles, temperature, which is measured in degrees Kelvin. So that's really important to note, is that the temperature is in degrees Kelvin as opposed to degrees Celsius. So that's really important to remember for any calculations involving pressure. The volume, which is measured in liters. So that's also really important to remember with calculations, is that it's liters, not milliliters, because many questions will give volumes in milliliters. So you want to make sure that it's in liters. And pressure. So that's going to be measured in kilopascals. And so when we're considering the number of gas molecules, we need to consider that increasing the number of gas molecules will subsequently result in an increase in the pressure. And so this is because if we have more gas molecules in a system, there's less space for them to uptake, and so they'll be all compressed in one area, which means that there's more pressure acting on them. And that's correlated with the volume. And so with the volume, increasing the volume will decrease the pressure, because as the volume of the container gets bigger, there's then more space for the gases to occupy. And so if there's more space for the gases to occupy, then they can move around more, they're more spaced out from each other, and so there's less compression onto those molecules. And so next we can look at temperature. So increasing the temperature will increase the pressure, and that's because when we increase temperature, we are increasing the movement of the molecules in the gas. And so when we're increasing the movement of the molecules of the gas, there's more kinetic energy, and so the molecules are more frantically moving around. And as they're more frantically moving around, it means that there's, at any given time, although there's the same amount of space in the container, it appears that there is less as the molecules are moving more quickly through that time. And finally, we've got pressure, in which the pressure will be affected by any of the above variables and will opposingly affect those variables. So with number of gas molecules, as those increase, the pressure will increase. With temperature, pressure will increase. And with increased volume, pressure will decrease. And then pressure will opposingly affect those variables. So if we increase pressure, we'll need to have less gas molecules in order to do that, or less gas molecules per the amount of area. For temperature, we'll need to decrease the temperature if we decrease the pressure. Same as if we decrease the pressure, it will decrease the temperature. For volume, we'll need to, if we decrease the pressure, it will increase the volume of the container which the gases are in. Same as if we increase the pressure, it will be a decrease in the volume that the gases are in proportionally. So now we have our gas laws. And so we have 4 main gas laws. And so we have 3 gas laws, which are individual gas laws, and then we have a combined gas law. And so the 3 gas laws which we have, which we combine, are Boyle's law, Charles's law, and Gay-Lussac's law. And so when these all are combined, we end up with what we call the combined gas law. And so these gas laws are commonly used to compare those variables which we talked about earlier and to show the proportional changes that occur mathematically. And so it can help us determine the volume of a particular gas, the temperature of a gas, or the pressure of a gas, if we know one or more of the variables. So Boyle's law is going to consider the volume that a gas occupies, and that will be inversely proportional to the pressure applied to it at a constant temperature. So our formula will be P1V1 equals P2V2. And so this is typically used if we want to find the pressure of a gas and we know the volume of the gas, or if we want to find the volume of a gas and we know the pressure of the gas. Our next one is Charles's law. So Charles's law is the volume, talks about the volume that a gas occupies and it being directly proportional to its temperature. And this is only applied when at a constant pressure. And so we will typically use this if we want to determine the volume of a gas based on the fact that we know the temperature, or if we want to determine the temperature of a gas based on knowing the volume. Our final one is Gay-Lussac's law. And so this is considering pressure and temperature. And so it's considering that pressure is directly proportional to temperature at a constant volume. So without changing the volume, if we increase pressure, we're going to increase temperature. And so we use this formula if we know the pressure, but we want to find the temperature, or if we know the temperature and we want to find the pressure. And so it's important to note that for all of these, they have to be used in conjunction with a reaction. So if we know a starting pressure, a starting volume, and then a finishing pressure, we could use Boyle's law to find the finishing volume. Or if we knew a finishing volume, a finishing temperature, and a starting temperature, we could determine the initial volume using Charles's law. Or for example, considering Gay-Lussac's law, if we knew a starting temperature, a finishing pressure, and a finishing temperature, we could determine the initial pressure. And so, as mentioned before, when we combine all of these, we get the combined gas law. And so, the combined gas law has a formula of P1V1 over T1 equals P2V2 over T2. And so this basically provides us with a combination of all of the above in order to then determine a multitude of different variables. And so I would say this is one of the most common ones which you will use when considering the gas laws, because it encompasses so many different factors that affect the gases. Another important thing we want to note is the molar volume of gases. And so this is because 1 mole of gas at standard temperature and pressure, so STP conditions, will occupy a volume of 22.7 litres. And so this will always occur regardless of anything other than the fact that it must be at standard temperature and pressure. And so this means that we can use this formula, which is N equals volume divided by 22.7. So this means that if we don't know the number of moles of a gas, but we know the volume, we can determine the number of moles. Or if we want to know the volume, but we know the number of moles, we can determine the volume using this formula. So we also want to consider this formula here, which is the ideal gas law. And so the ideal gas law is PV equals nRT. And so the combined gas law is containing all 4 variables which we looked at before. So that being temperature, pressure, volume, and number of molecules. Then we also need to consider that we're considering Avogadro's number. And so that's that 1 mole of gas occupies 22.7 litres at STP. So STP being 101.3 kilopascals and 270 degrees Kelvin. And so incorporating this value is going to yield the ideal gas law. And so we can see in our ideal gas law, P is going to be the pressure in atmospheres. V is going to be the volume in litres. N is going to be the number of moles. R will be the universal gas constant. And so the universal gas constant is basically just a constant which represents the amount of gas raising a temperature per mole. And so that's 8.3145 joules per mole per degree Kelvin. And then we have temperature, which we need to importantly remember is in Kelvin. And so there are variations from the ideal gas law, and so we briefly spoke about this before, but we're going to consider this in more detail. So gases will behave in an ideal way under high temperatures and low pressures. And so the gases will depart from these ideal conditions at low temperatures and high pressures, because this is going to violate the assumption that there is significant space between the molecules and that their volume is negligible. So we can plot this differentiation by comparing PV over RT to the pressure. So that's comparing the pressure times by the volume divided by the universal gas constant and our temperature. And so that can then be compared with the pressure as a proportional value, and that helps us to determine what our departures from the ideal gas constant will be. And so we can see based on this diagram here, it's actually really hard to achieve the ideal gas conditions as it only occurs for a very short amount of time. And so it will only occur at a pressure of 0, and then for some other gases occurring at various other pressures along the way, but only for a very brief amount of time. So we can see that there is often variation from the ideal gas law, and the ideal gas law is often not followed through. We're now going to go on to looking at aqueous solutions. So aqueous solutions require us to look at water, because water is our universal solvent. So whenever we're typically considering solubility or anything that's dissolved in a solvent, we're typically looking at water, because water dissolves most polar solutes. And so water is a bent triatomic molecule, which we looked at before. And so this means that it's got its lone pair at the top, and we know that it has 2 highly polar covalent O to H bonds. And so this means that water has a very strong net dipole, and means that it can participate in 3 different hydrogen bonds. So it can participate in a hydrogen bond from the oxygen molecule, where the electrons are centered to, or it can participate in hydrogen bonding from either of the hydrogen atoms, where the protons are centered to. And so we can see that down this bottom left diagram here, where we can see these hydrogen bonds forming this web-like structure due to the attractions. And so the high boiling point of water compared to molecule size and its unique density and surface tension properties are going to be due to this structure. So surface tension is referring to where we have this hydrogen bond web-like structure, and it provides a tensile surface in which stuff can balance along, such as when you see a leaf floating along water, that is due to surface tension. And so when we're considering water, we can see that water has a very high boiling point, a very high melting point in comparison to other substances, despite those other substances having a larger molar mass. So for example, we've got H2O has its molar mass of 18 and its melting point is 0 and boiling point is 100 degrees. But if we consider something like our next molecule down, we've got a molar mass of 20. And so a molar mass of 20, we would assume it's a bigger molecule, it's going to have stronger intermolecular forces. However, this is just a single atom, so it actually has a very low melting point and a very, very low boiling point. And so in comparison with water's very, very strong, intermolecular forces with the hydrogen bonds, it's got a much higher melting point and boiling point. We can then consider something like methanol, which has its molar mass of 32. And so we can see methanol has a hydrogen bond because of that O to H, and it has a lot larger molar mass, so it's also going to have larger dispersion forces. However, it has a much lower melting point and a much lower boiling point than water, and this is because water has 2 locations of hydrogen bonds, whereas methanol only has 1 location of a hydrogen bond. And so this means that the water molecules can be more attracted to each other than methanol molecules can be attracted to each other. And so this means that there is going to be harder to break apart those water molecules, so there'll be a higher melting point and subsequently a higher boiling point. So when we consider solvation in an aqueous solution, solvation is the process where we're going to be dissolving it. So the solvent is the most abundant of the substances in a solution. So when we're considering a sodium chloride solution, we will have more sodium chloride and it will be the most abundant typically in the solution. And so the solute will be dissolved in the solvent. So the solvent, for example, is the NaCl being dissolved. The solute is the NaCl being dissolved in the water solvent. And so the same dynamic interactions that give water its properties are what enable it to be such a good solvent of polar substances. And so it will only be polar substances because it's like dissolves like. And so solvation is considered to be the process in which solvent molecules surround solute molecules and cause dissolution. So solvation is going to be where we're having those water molecules break the intermolecular forces of those NaCl molecules and then reform intermolecular forces fully surrounding it. And so that's then the dissolution part. So dissolution is being underpinned by thermodynamics. So this is because we need to be able to break the solute to solute interactions in order to allow solvation to occur. So we will have some instances in which the solute to solute interaction is going to be so strong that it cannot be overcome by solvation. So if we have a molecule with extremely strong intermolecular forces, those intermolecular forces will not be able to be broken apart such that it then won't allow for for the solubility to occur and the solvation to occur, because it won't be able to be intermixed with the water solute, with this water solvent. And so that would only typically be if the particular solute which was being dissolved in the water solvent had stronger intermolecular forces than that of the water. But because water has such strong intermolecular forces, it's very difficult for there to be a solute in which it has stronger intermolecular forces than water, because water is used as our universal solvent for that particular reason. So typically that doesn't tend to occur. And so when we're considering aqueous solutions, we also need to consider the mole concept. And so this is relating the mass, number of molecules, molar mass, and number of molecules in solution to describe aqueous solutions. And so the sum of the molar masses of all atoms in a substance can be used to determine the molecular or formula mass. And so 1 mole of the quantity, 1 mole is going to equal the quantity of a given substance that contains an equal number of molecules as 12 grams of carbon-12. And so carbon-12 is like our measurement point. It's our standpoint where we use that to determine moles, basically. And so carbon-12 has 6.02214 times 10 to the power of 23 molecules we consider. And so that's talking about like relating back almost to Avogadro's number. And so it's the quantity of any given substance that's going to contain an equal number of molecules as that 12 grams of that particular carbon-12. And so we can then apply this to this formula which we have, which is molar mass equals mass over moles, or otherwise known as moles equals mass over molar mass. And so we can also figure out molarity when we're doing aqueous solutions, where we use molarity equals moles of solute divided by liters of solution. And so that's represented as C equals N over V. And so this is used to determine the concentration of a particular substance. So it's basically our concentration is equaling the number of the moles of the solute which we've put in to the solution divided by the total volume of the solution which we have. And so we also use this concept or this formula of C equals N over V. And so, C1V1 equals C2V2. And so this is used for dilutions. And so C1 and V1 are going to be characteristic of our starting solution, whilst C2 and V2 are going to be characteristic of our finishing solution. And so this can be used, for example, if we're starting off with our solution of NaCl in water, and we know that we start off with a concentration of 1 molar and we have 10 mils of our solution. So we'd have 1 times by 10, and then we know that we're adding in, so we'd have 1 times by 0.01 because it's in liters. And then we know that we're adding in 100 mils of water. So we're going to end up with 110 mils of solution. But we want to determine how is that going to affect the concentration of the solution which we have. Because we know our solution which we currently have is 1 molar, but how is that going to change when we add more water? So we go 1 by 0.01 equals C2 times by 0.11. And so we can then rearrange this algebraically and determine our concentration. And so we would divide it out, and I'll just quickly do it on a calculator to give you an answer just for completion. So we'd have 1 times by 0.01 and then divided by 0.11. And so that gives us a finishing concentration, or C2, which equals 0.091. So we'd say that our final concentration of this solution after we've added that volume of 100 mils to the initial solution is going to be 0.09 molar. So these are some common exam style questions which we typically see. And so I've just got these here with a working out below, just so I can step you through these, because I think it's really important to understand the foundations of how you figure these out and how the calculations should be structured. So first of all, we need to start off with what mass of CO2 is produced. So the first question, what mass of CO2 is produced by the combustion of 1 mole of CH4? So this is a really good starting question, because it's very common to get exam style questions like these, because they want to see that you can apply ratios, and that you can apply that mass equals moles over molar mass. Moles times by molar mass. So that rearrangement of that formula. So in this question here, they've actually given you the equation of the reaction, and so that's really good. Often they won't do that, but we can see here that the reaction which we have occurring here is we've got CH4 plus 2O2 is making carbon dioxide and water. And so it's really important to note that we do have ratios in these, so we need to see, are the ratios something that we need to apply in this? So we're looking at CH4 to CO2, and we can see that those have a 1-to-1 ratio of CH4 to CO2. So we don't need to worry about any multiplications with these, because they are a 1-to-1 ratio. So the only thing we need to consider for this is we know that we're putting in 1 mole of CH4. So because we maintain a 1-to-1 ratio, with that 1-to-1 ratio, we can see that if we have 1 mole of CH4, we will produce 1 mole of CO2. So we want to calculate, if we know we're producing 1 mole of CH4, we want to see how does 1 mole of CH4 turn into a mass. So we can use mass equals moles times by molar mass. And so we know that the number of moles is 1. So we can do 1 times by, and then the molar mass of carbon dioxide. And so we can use our periodic table for that. So we can find the molecular mass of carbon, which is 12, and then the molecular mass of oxygen, and there's 2 oxygens, which is 16. So we've got 1 times by 12 plus 16 plus 16. And so that's going to give us an answer of 44, which means that there is 44 grams of carbon dioxide produced when we combust 1 mole of methane, or 1 mole of CH4. Our next question which we're going to look at is how many moles of HCl can be produced from 0.226 grams of SOCl2. And so again, they've given us the equation here, but typically in an exam, they would tend to want you to write the equation yourself. But the equation is always the first step if it's not written for you. And so that's SOCl2 plus H2O makes SO2 plus 2HCl. And so another thing we've got to do again is we've got to look at our ratios. So we can see we want to figure out how many moles of HCl can be produced from 0.226 grams of SOCl2. So we can see that there is a 1 to 2 ratio of HCl. So we just got to take note of that for now. We'll come back to that because we've noticed that there is grams for SOCl2. And so we can't do a complete comparison with grams because grams are not a comparable value when we're looking at chemical reactions, because the number of grams will change depending on what the substance is. So we need to convert to moles. And I think a good thing to remember is, if in doubt, convert to moles. So if you don't know what's happening in the reaction and you don't know where to start, I think that always the best thing to do is convert to moles, because typically it will require moles in order for the reaction to be calculated. So we'll use the moles equals mass over molar mass formula. And so that's going to be our mass of 0.226 divided by the molar mass of SOCl2. So that being 32.1 plus 16 plus 35.5 plus 35.5. And so when we do that on a calculator, that gives us an answer of 0.0019 moles of SOCl2. And so now that we've got that value in moles, we can now use our ratio, which we talked about earlier. So remembering that we have a 1 to 2 ratio of SOCl2 to HCl. And so that means that there is going to be double the number of moles of HCl produced that we started with of SOCl2. So that means we've got to do the 0.0019 moles of SOCl2 times by 2, which will give us 0.0038 moles of HCl. And so we know the number of moles that have been produced is 0.0038 moles of HCl. And so that's all that the question has asked us for. So we could leave the answer as that. And in an exam, I would say leave the answer as that. That's all you need to do. They've only asked you for moles. If they asked you for grams, though, we have the next part of the equation. And so we'll just do that we'll just do that to finish it off and just for completion. And so because typically in an exam, they will ask you to convert back to the units which you started with. And of course, the units which you started with were grams. So they typically want you to convert back to grams. So in order to convert back to grams, we'll use mass equals moles times by molar mass. And so that's going to equal our moles of HCl, so 0.0038, times by the molar mass of HCl. So that's going to be 1 plus 35.5. And so then that's going to give us 0.139 grams of HCl. And I think that's really important to note because that really shows how important it is to remember to convert to moles. Because remember, we started off with 0.226 grams of SOCl2, and we doubled that amount we produced double the amount in terms of HCl, but we've got a lot less, we've got 0.139 grams of HCl produced. So although we've got a 1 to 2 ratio of SOCl2 to HCl, we've actually got less quantity of HCl produced, but more moles of HCl produced. We're now going to go on to talking about solubility, and so this links in quite well with our concept of aqueous solutions. And so first of all, you need to become very aware of the solubility table. So the solubility table is present in your data booklet, and it's going to be a lifesaver for you. It's very useful. And basically it's just this big table which tells you what is able to be dissolved in what. So it tells you the ion, whether it is soluble, and what the exceptions to the rule are. So for example, if we consider the nitrate ion, it is soluble in every circumstance because there are no exceptions to the rule. However, if we consider the chloride ion, we can see that the chloride ion is soluble. However, if we have AgCl or HgCl2 or PbCl2, they will not be soluble in water. And so that's because they are exceptions to the rule, which means that they will form our substances which are not dissolved. And so another important thing to note is that the lead halides, so for example PbCl2, which we just discussed, will be soluble in hot water. And so that also goes for PbI2, that will also be soluble in hot water. But in our typical standard temperature pressure conditions in the lab, they will not be soluble. Another thing important to notice is that calcium hydroxide is slightly soluble in water. So we say that it's an exception to the rule with the insolubility of the hydroxide ions. However, it is only slightly soluble in water. So it doesn't have a full extent of solubility. So that means that at very low concentrations, calcium hydroxide may be soluble, but at higher concentrations, it won't be soluble. And so with solubility, we can consider precipitation reactions. And so precipitation reactions are the combination of two solutions containing dissolved ions, and this yields a reaction depending on the reactivity of each ion. And so this is often true for acids and bases, but the products will be different. And so if the product of the reaction is not soluble in water, it will rapidly precipitate out, and as it's called a precipitation reaction. And so this will produce what is known as a precipitate. And so that's the solid which you can see which is sometimes formed in particular reactions. And so you must incorporate the solubility rules to determine if a precipitate will form. And so that's using our table from before. And so you can determine if the products, say for example you have AgCl as a product, you will know that that's an exception to the chloride ion rule, and so hence there will be a precipitate or an AgCl solid that is produced in the reaction. And so these reactions are always single or double displacement reactions. So an example which we have here is the combination of two solutions containing silver nitrate and sodium chloride. So if we have a silver nitrate solution, AgNO3, and we add that to the sodium chloride solution, which is NaCl, we then have this displacement reaction in which we produce AgCl and NaNO3. And so when we look at what our products are, we can see we've got AgCl and NaNO3. So we want to look at our solubility table to determine if these are soluble. So we can look for Cl, and we can see Ag is an exception to the solubility of chlorine ions, and so we know that AgCl is not going to be able to be dissolved. It will be insoluble, and so it will be a precipitate. Then our other one was NaNO3. So when we look for Na, we can see it is the sodium ion, it is soluble, and it has no exceptions to its rule. So that means regardless of what is bonded to a sodium ion, it will be soluble. So we know that that will be soluble in water, the NaNO3, and so it will form into the aqueous state. So we know that AgCl, or sodium chloride, will be our precipitate. Next up, we want to consider the net ionic equations. So we can write net ionic equations for solubility reactions. And so that's involving only the species that are involved in forming the precipitate. So they're essentially double or single displacement reactions in which we're defining the states of matter and the way in which they change. So we can define the net ionic equation by separating the soluble, so aqueous reactants, and products into their ions. And for those ions which don't participate in the reaction, we call those spectator ions, and they get removed from the reaction. So when we're considering the combination of the two solutions containing silver nitrate and sodium chloride, we know that the sodium and the nitrate ions don't participate in the reaction as forming a solute, as forming a precipitate, because they are soluble and so just dissolve into the solvent. However, we know the Ag ions, so the silver ions, and the Cl- ions, so the chlorine ions, combine to form the the silver chloride. And so the silver chloride, we know, forms a solid precipitate. And so because it forms a solid precipitate, we can say that that is what's going to be included in the net ionic equation. So our net ionic equation will be Ag plus Cl minus makes AgCl solid. We're now going to go on to talking about acids and bases. So we want to consider the concept of the Arrhenius acids and bases. And so this is discussing how that we have dissociation of acids and bases in solution. So I believe you probably would not have covered this yet in class, or you may have only have just begun to learn this. So I accept that this is a relatively new concept, but I am showing you this so that you have some preparation for these concepts which are to come, and so that you are hopefully well prepared for this topic. And so in aqueous solution, acids will dissociate. So acids are going to dissociate to form hydrogen ions, which we can otherwise call protons, and anions. And so the more dissociation, the greater the strength of the acid will be. So for example, if we consider a strong acid like HCl, in water, we know that HCl can dissociate and lose a hydrogen atom to the water, and so the water will gain an electron to form H3O+, which is characteristic of an acid. So acids will form H3O+, or H+, and then we'll have left behind the chlorine ion. And so this can also be written as HCl dissociates into H+ and Cl-. And so this is just showing that it has full dissociation because it is a strong acid. But when we consider bases, they're going to do the exact same thing. So bases, except forming hydroxide ions. So bases are going to form hydroxide ions when dissolved in water, because they can either dissociate due to containing the hydroxide ion. So for example, sodium hydroxide, which is a very strong base, can dissociate into Na+ and OH-, and so the OH- is what is characteristic of a basic solution. So it has that OH- because it is basic. Or they can react with water to accept a proton, which then produces the hydroxide ions. So for example, if we had NH3 and we added that to water, we would then get NH4+, which is ammonium ion, plus OH-, and so that OH- would be the leftover from water. And so then that, because we have the OH- present, it's showing that we have the hydroxide ion being produced. And so ammonia, or NH3, is a weak base, and so it does not have a full extent of dissociation. So that's why we can see that we have a reversible arrow for the ammonia reaction, where the water is accepting a proton, because the reaction can be reversed to go back the other way because we don't have full extent of dissociation. Whereas if we're considering the sodium hydroxide, that has full dissociation because sodium hydroxide is a strong base. And so when we consider the strength of acids and bases, we need to consider this concept of strong and weak versus concentrated versus dilute. So we can have strong acids, and you may think a strong acid is the same as a concentrated acid. But as a matter of fact, they are very different, because strength of an acid and base is going to relate to the proportion of dissociation. So the amount at which those atoms have split. So for example, the hydrogen chloride ions or the hydrochloric acid ions, or HCl, have split into H plus and Cl minus. And so a strong acid or base is going to have a greater extent of dissociation. So for example, HCl is going to mostly split into H plus and Cl minus in aqueous solution. Whereas if we compare that with something like ethanoic acid, which is a very weak acid, we can see in this diagram here, we have a very limited extent of dissociation. So most of the ethanoic acid molecules will remain as the original ethanoic acid molecules in solution, and very few will split into the CH3COO- ion and the H plus ion. Then when we consider concentration of acids and bases, and we consider concentrated versus dilute, concentration is going to refer to how much of the original substance is going to be dissolved in the aqueous solution. So if we have a lot of the acid molecules in the solution, regardless of whether it's a strong acid or a weak acid, we can see, like this one here on the right at the bottom, we've got a concentrated solution because there is lots of these molecules of the acid, regardless of whether it's a strong or weak acid, there's lots of them in that solution. Whereas a dilute solution, we have very few of those acid molecules in the solution, or base molecules in the solution. And so that's going to mean that because there's so few of them, we consider it to be dilute. So that's just something very important to consider when talking about the properties of our acids and bases and knowing what a strong acid or a strong base is. So now we want to talk about the self-ionization of water, because water spontaneously self-ionizes to a very minor degree. And so this is because hydrogen ions associate with water molecules to yield what we call hydronium ions. And so hydronium ions can act as a protein donor, whilst hydroxide ions remain free in solution. And so acidic or basic solutions will rapidly increase this degree of ionization. So when acidic and basic solutions combine, the hydroxide and hydrogen ions yield to water and the solution neutralizes. So this often yields a salt as a product. So we can see our equation here. We've got H2O plus H2O, so basically water plus water, is going to produce hydronium and hydroxide. And so at 25 degrees Celsius, or at our STP temperature, the number or the proportion of hydroxide ions is going to be equal to the proportion of hydronium ions, and so that's going to equal to 1 times 10 to the power of minus 7 molar. And so that can help us determine concentrations of hydroxide ions and concentrations of hydronium ions in order to determine concentrations of our acids and bases. So when we look at the pH scale, pH is going to be a measure of how acidic or basic a solution is. And so pH is the negative logarithm, so in base 10, of the hydrogen ion or hydronium ion concentration. So we can consider it to be pH equals the negative log of the concentration of H+, or pH equals negative log of the concentration of H3O+. Whereas we also have this concept of pOH. And so pOH is the negative logarithm in base 10 of the hydroxide ion concentration. And so that's going to be our OH minus ions. And so the formula for pOH will be pOH equals negative log of the hydroxide ion concentration of the solution. And so as the hydroxide and hydrogen ions associate to yield water, and the formulas can then be used interchangeably. So the maximum we have is 14 and the lowest being 1. So the maximum 14 is representing the lowest hydronium ion concentration when we're looking at pH, when we're looking at pOH, and so the formulas can then be used interchangeably. So in any solution at 25 degrees Celsius, H3O plus times by OH minus will equal 1 times 10 to the power of minus 14. So we can also use that to determine concentrations of hydroxide ions and hydronium ions at 25 degrees Celsius if we don't know the concentration of one, but we know the concentration of another. And so this can help us convert between pH and pOH. We also have these formulas of pH equals 14 minus pOH and pOH equals 14 minus pH, which just helps us to easily convert between these. We also have some important reactions of acids which we need to consider. And so these are very important to remember. And also an important note is that salt is considered to be any ionic substance. So any ionic substance which is produced in a reaction is considered to be a type of salt. So our first reaction which we have is acids react with most metals to produce salt and hydrogen gas. So that will be 2HCl, as an example, 2HCl plus Mg, so magnesium, is going to make magnesium chloride and hydrogen gas. So that's where the acid is hydrochloric acid, the metal is magnesium metal, the magnesium chloride is the salt, and the hydrogen gas is obviously the hydrogen gas. We next can have acids react with metal hydroxides, so bases, to produce salt and water. And so this is known as a neutralization reaction because the acid is being neutralized by the base, or the base is being neutralized by the acid, and so they cancel each other out. And so an example of this is hydrochloric acid plus magnesium hydroxide makes magnesium chloride and water. And so in this case, the acid is the hydrochloric acid, the base or metal hydroxide is the magnesium hydroxide, and then the salt is the magnesium chloride. And then of course we have water produced as well. Finally, we have acids reacting with metal carbonates, and this produces salt, water, and carbon dioxide. And so an important thing to note about this reaction is that it produces carbon dioxide, and so you will notice gas and bubbles being produced if you conduct one of these reactions. And so an example of this is if we have hydrochloric acid and magnesium carbonate, and we can combine those to make magnesium chloride, water, and carbon dioxide. And so this is where hydrochloric acid is the acid, magnesium carbonate is our metal carbonate, magnesium chloride will be the salt, and then we've got water and carbon dioxide. Now, our last thing that we want to look at before we finish up is considering rates of reaction. So rates of reaction are the rate at which a reaction occurs in terms of either minutes or something per minute or something per second, and it's ultimately going to be underpinned by thermodynamics. And so the reaction conditions refer to the environmental conditions and the lab conditions that affect reaction rate. So the main ones for these are temperature, pressure, and presence of catalysts. So temperature, when we consider temperature, higher temperatures may increase the reaction rate. And so this is because they will increase kinetic energy because we're putting more energy in as heat, and so there's more energy for these particles, so they're going to move around more, and so when the particles move around more, they're more likely to collide, to react, and then create a product. And so remembering they have to collide at the correct orientation at or above the activation energy in order to form products. So if there is this increase in kinetic energy and more collisions, it is more likely that the reactant particles will collide to then form products. With pressure, higher pressures can increase the reaction rate, and this is because at a higher pressure, there's a smaller area for the reactants to occupy. So if we're considering a gas, we've compressed the gas down into a smaller volume. So this is also associates with volume. So smaller volume will increase reaction rate. And so that's because we've compressed it down into a smaller area. So the molecules are moving around and they're going to have a smaller space to move around. So they're more likely to collide to form products. And they're also more likely to collide at or above the activation energy because higher pressure equals higher temperature, and so there'll be greater kinetic energy. There's also more rebound off the sides of the container which it's inside, and so that means that there's more kinetic energy from that, and so they're more likely to collide at or above that activation energy and at that correct orientation to form products. And finally, we have catalysts. And so catalysts will increase the reaction rate because catalysts can either work by lowering the activation energy for the reaction. So this will mean that if the activation energy is lower, less energy is required when those molecules collide in order for a product to be produced. It can also hold the reactants in the correct orientation so that they will collide at their active sites, resulting in a functional product being produced. And that's because the molecules can collide at the correct activation energy, at or above that activation energy, and still not form products if they haven't collided on the right orientation. So having a catalyst which holds it in the right orientation ensures that when they do collide at that activation energy, they will definitely go on to form a product. And so when considering temperature and pressure, we can consider that all reactions can either be exothermic, so releasing heat energy, or endothermic, and so that would be taking in heat energy. And so some reactions may do work on the environment by producing more moles of gas via expansion. And so we can write the heat energy or work as pressure, or as a product, or as a reactant. And so we can see, for example, here, with these here, we have delta H, which is our value. And so a negative delta H value is going to mean an exothermic reaction. And so that means heat is being produced, and so we consider heat like a product. Whereas we can have an endothermic reaction, and so an endothermic reaction will have a positive delta H value, and so that means that we are absorbing heat for the reaction to occur, so we're using heat in order for the reaction to occur, and so we're considering heat to be like a reactant. We also want to consider activation energy and our catalysts. So all reactions have an activation energy, regardless of whether they are a spontaneous or a non-spontaneous reaction. And this activation energy has to be overcome for the reaction to occur. And so often a lot of reactions occur at a very, very slow rate because it's very unlikely that the activation energy is reached by any of the molecules. But catalysts can be used to speed up this rate of reaction by binding to the reactants and facilitating the formation of products, because they don't participate in the reaction, but they provide an alternative reaction pathway by lowering the activation energy so that it's easier for the activation energy to be reached, or holding it in the right direction so that the active sites can be collided. And so we can see on the left here we have a non-spontaneous endothermic reaction, and we can see when we have this rate of reaction, we have less energy in the reactants, more energy in the products. And then with an exothermic reaction, we have more energy in the reactants, less energy in the products, showing that energy is being released. So that brings us to the end of what we have for today. So the key skills which we learnt today was we learnt about the valence shell electron pair repulsion theory. We learnt about polarity. We learnt about intermolecular forces, gases, aqueous solutions, solubility, acids and bases, and rates of reaction. So these are sort of like the main skills that you really want to be making sure that you're on top of coming into Unit 2. And then a few little reminders before we finish up is that although this may all seem quite overwhelming at the moment, there's plenty of learning to do and plenty of practice to be done. So as long as you keep practicing, it will help you improve. And then my other final reminder is don't forget about the data booklet. There are so many useful things in the data booklet which are very important and are required for an understanding of all these different topics. So make sure you're using the data booklet and make sure you're utilizing all of the formulas and concepts which they give you in the data booklet. So thank you everyone for watching, and good luck with this year, good luck for next year, and I hope you all enjoyed. Thank you.